All right. So welcome to the session on signatures, signature schemes 1. We will have 1, 2, 3 talks coming up on signature schemes.
So this one don't use?
Well, it's gonna be so.
Oh, it's gonna be, okay. Then I won't go with it.
Is it okay?
Yes.
Okay, so the first talk will be on the paper A Lower Bound on the Length of Signatures based on Group Actions and Generic Isogenies by Dan Bonnet, Jiaxin Guan, and Mark Zandri, and Jiaxin will give the talk. Okay.
Thank you, Chair, for the introduction. Hi, everyone. So my name is Jiaxin Guan, and today I'll be talking about a lower bound on the length of signatures based on group actions and generic isogenies. So to start off, first of all, why are we interested in these signatures that are based on group actions and generic isogenies? Well, let me tell you a story. So I was applying to renew my US visa, and the visa officer was looking at my CV and then asked me the question. So what is post-quantum cryptography? I said, okay, good question. Let me tell you the following story. And this is a story I told. So in cryptography, we have our favorite friends, Alice and Bob, and they love to do all sorts of interesting protocols between them, and we require certain security properties of these protocols. And the way we do this is via security reduction, we reduce these security properties down to certain hardness assumptions. So if an adversary comes over with his own computing resources, as long as the adversary cannot break these hardness assumptions, the security of these protocols are guaranteed. However, suppose the adversary now has access to a quantum computer. Then actually a lot of the hardness assumptions that we use nowadays will be broken. For example, the hardness of the RSA, hardness of factoring, discrete log, so on and so forth. And as a result, the security guarantee of these protocols will be gone. So this is exactly what we study in post-quantum cryptography. We want to construct schemes based on computational assumptions that are resistant even if the adversary has access to a quantum computer. And so far in the literature, most of the constructions in post-quantum cryptography are from lattices. But you know, we cryptographers are usually paranoid, and we want not to put all of our eggs into a single basket. Right? So just in case in the future, let's say if there's some attack on a lattices, we want there at least to be some alternative that we can resolve to. So ideally, we would want some sort of a second basket, though it might be a little bit smaller, but at least there's somewhere that we can put our eggs in. And it turns out, yeah, there is such an alternative, and this is exactly group action-based cryptography. So this was the story I told the visa officer, and the visa officer seems very confused and thought for 20 seconds, and they say, okay, that seems like very important research problems, so we're going to need to do some additional checking on your visa status to make sure you're not a spy or something. That's how I end up stuck in Canada for a month before returning to the US. So, but that story aside, so what are group action-based cryptography? Well, cryptographic group actions consists of 3 components. So first of all, you have a group G and a set X, and an operation that allows you to have a group element G acting on a set element, and the output is another set element. We require several properties of this. So first of all, you can think about this as the star operation as sort of the exponent in a normal group. So you're essentially raising a set element to the power of a group element. And we require several properties. So first of all, we require there is a group identity, E. So it's a group element that is an identity. So if you apply this group action on any set element, it gives you back the same set element. And we also require compatibility or composability, essentially saying that if you apply 2 group actions on the same set element in sequence, then you can compose these group actions together and perform a single group action on the same set element. Notice that we can imagine also other properties of the group action. For example, you can imagine a group actions to be abelian, but these are the only bare minimum requirements that we have in order for our lower bound to go through. So the hardness assumption that we have here for group actions is the discrete log for group actions. So if you're given 2 set elements in which one of them has a discrete log against the other, so in this case, y is equal to g star x, it's very hard to find the discrete log between these 2 set elements. Notice that you can think about this if you were translate this to normal group, then what you will have is y is equal to x to the g. So g is the exponent. So we know that discrete log within groups, they are pretty much broken if the adversary has a quantum computer. So the adversary can use Shor's algorithm to quickly find the order of the group, and then everything is broken from there. But notice that in the case of group actions, the things that we're exponentiating here are set elements, and there's no equivalent efficient group operations between these set elements. So Shor's algorithm will not work here. So far, the best quantum algorithms that we have that solves the group action discrete log is sub-exponential. Okay, so now you might be asking, okay, so this is a group action-based cryptography. How could we instantiate such a group action? So it turns out that one of the possible ways to instantiate a group action is through isogeny-based cryptography. I won't go into too much detail about isogeny today. We won't be able to cover in 20 minutes, not even like 2 hours or 20 hours. But roughly speaking, a one-sentence summarization of isogenies is that an isogeny is a sort of a mapping between two elliptic curves. And it's been shown by Kuvignus and Rostotsev and Stobanov that we can actually obtain group actions from these isogeny graphs of elliptic curves. And later on, there has been this specific type of isogeny graphs called supersingular isogeny graphs, where we see constructions of key exchanges from. And one of the purpose there is to avoid the sub-exponential quantum algorithm for discrete log, as we saw on the previous page. However, as we have already seen in yesterday's best paper section, there has been recent attacks on key exchange protocols that are based on the side assumption, supersingular isogeny Diffie-Hellman. And we've already heard about this in yesterday's best paper section, so I won't spend too much time here. But the general idea I want to point out is that, first of all, a side itself is not a group action. And secondly, while side and psych, which is built upon side, is pretty much dead, but it doesn't seem to affect other isogeny-based protocols, for example, C-sign, C-fish, or ski-sign. So this means our lower bound that we show in this paper is still meaningful. Okay, so now we're going to move on to the actual lower bound, so where we show a lower bound on the length of signatures. So the motivation here is pretty straightforward, right? In the classical world, signatures can be really short. For example, the Schnorr signatures are really short, so if we want 128-bit security, a Schnorr signature only needs to be 96 bytes. So for security parameter lambda, the signature length can be as small as 3 lambda, which is really surprisingly short. However, for post-quantum signatures, if we look at the NIST has a call for post-quantum signatures, if we look at the final lists, all of them sizes are at least thousands of bytes. They're nowhere in comparison with the Schnorr signature. So the natural question is, are there any Schnorr-like signature schemes that are post-quantum secure, and what's the shortest that we can get? So far, the shortest we get is from C-fish, and C-sign, and the C-sign itself still requires 3 kilobytes for the signature size plus the public key size. That's not as close to the Schnorr signature. And in fact, in this paper, we show that this is no surprise. So in this paper, we want to arrive at a lower bound for group action-based, for the length of group action-based signatures. And we have two options for us to work in. We can either work in Morris generic group model, or we can work in Shoup's generic group model. But there are some slight issues with either approach. So for Morris generic group model, it has been shown by Dutelin et al. That signatures are actually impossible in Morris generic group model. Essentially, there you can think about you can have an algebraic combination of signatures, and that will allow you to make a forgery. And in terms of Shoup's generic group model, it has been shown by Zandri and Zhang that the Shoup's generic model actually implies random oracles. So we're sort of in a conundrum here. So on one hand, we can either choose to work in Morris model, where we prove a lower bound for signatures, which are impossible. So we're proving a lower bound for something that's impossible, and which doesn't really make sense. Or we can choose to work in Shoup's generic group model, and in there, we're essentially trying to solve the open problem of proving a lower bound for random oracle-based signatures. So what do we do? Okay, So we make the observation that while signatures are impossible in Morris model, however, identification protocols, these are actually possible in the Morris model. So what we do instead is we prove a lower bound for group action-based ID protocols. So this is a bound we have, lambda squared over log lambda, and we make the observation that the state of the art, all of the constructions of group action-based signatures actually are obtained by constructing a group action-based identification protocol first, and then applying transformation, for example, Fischer-Shamir or the transformation by Unruh et al. But these transformations, they preserve the lower bound. So therefore, our lower bound transfers from these ID protocols to the group action-based signatures. So what is an ID protocol? Well, it's very similar to a signature scheme, except that there is no message for it to sign. So we have the prover, and the prover has the public key and the private key, and the verifier has only the public key. And the prover will try to communicate with the verifier into convincing the verifier that it has hold of the private key. And in this case, we're dealing with group action oracles, so each party, they have access to a polynomial number of queries to the group action oracle. So through this communication, the verifier is going to output 1 or 0, signifying whether the verifier believes that the prover actually has the private key. So security is defined in terms of an adversary, and the adversary is given a number of transcripts of previous communications between the prover and the verifier, together with access to the group action oracle. And the verifier is going to communicate with and the adversary is going to communicate with the verifier, and the adversary will win a game if the verifier outputs 1. And we want this probability to be negligible, and this is what we call the soundness error of the identification protocol. So the main theorem that we prove is actually a lower bound on the soundness error of a public coin identification protocol based on group actions. And in here, the lower bound, the soundness error lower bound is dependent on the completeness C, and P is the number of set elements in the public key. You can now think about this as the length of the public key. And the number of set elements in the transcript, and the transcript, you can think about when it transformed to a signature scheme corresponds to the length of the signature. And also it's dependent on the number of transcripts that the protocol should be secure against. Okay? So what does this bound mean? So if we think about the case, if we want unbounded, if we want security against an unbounded number of transcripts, so in other words, we set T to be large, in this case, this bound becomes S is greater than or equal to P to the minus N, where P is the number of set elements in the public key, and N is the number of set elements in the transcript. And if we want to achieve a soundness error, say, for example, 2 to the minus lambda, while at the same time, we want to minimize the size of the public key plus the size of the transcript, what we have is, as a result, is P plus N is greater than or equal to lambda over log lambda. And because every set element is lambda bits, if we multiply this by lambda, we get our lower bound, lambda squared over log lambda. On the other hand, you see that here we're actually adding up the size of the public key and the size of the transcript. So you might be wondering, you said it's a lower bound on length of signatures. Why do you include a public key? Well, because it's trivially, it's possible to get a signature scheme or an identification protocol where the transcript contains 0 set elements. So in other words, it's possible to have n equal to 0. But in this case, then P to the minus N is just equal to 1. And the bound now becomes S is greater than or equal to C minus P over T. So if we want a reasonable soundness error in this case, we would ideally need to set P, the number of set elements in the public key, to be almost as large as T, which is the number of transcripts that the scheme is secure against. So this sort of like matches our intuition, right? Because if you don't send anything in a transcript, then essentially you need to consume a set element in the public key for every transcript. Okay? So next up, I will give you a very quick overview of sort of how our proof goes through. It's a very high-level intuition. By no means it's rigorous. Just give a like proof of concept idea. So we will imagine that the ad is Bob, and we look at the public key, and imagine there are P number of set elements in the public key. And they're going to do the communication, and we look at a transcript, and there are going to be n number of set elements in the transcript. And now we're going to look at whenever the verifier makes a query to the group action oracle. And let's say the verifier makes a query to the oracle and gets response, A1 is equal to H star X1. So if we look at this query, that means this verifier now knows the discrete log between the set element A1 and X1. Correspondingly, we will build a graph of these set elements in the transcript and in the public key based on these queries. So in this case, we will connect an edge between the set element A1 and X1, meaning that the verifier knows the discrete log between these two nodes. And say it makes another query, A1 is equal to H prime star A2. We add another edge for A1 and A2, between A1 and A2, so on and so forth, until we deal with all the queries that the verifier makes. Now, if we think about this, notice that because the group actions, they compose, so if the verifier knows the discrete log between A1 and X1, and also A1 and A2, then the verifier knows the discrete log between X1 and A2. So in other words, if two nodes are in the same connected component, the verifier knows the discrete log between these two set elements. So in other words, if we color all of these connected components into different colors, then for any two set elements that are the same color, the verifier knows their discrete log. Okay? So now an adversary comes over, and we imagine we can build the following adversary. So the adversary does a very simple thing. The adversary now needs to simulate a transcript for the verifier. And for every set element that the adversary needs to simulate within the transcript, the adversary will just need to guess its color. And if it's guessed its color correctly, then the adversary can just sample the set element in a way such that the adversary knows the discrete log between this set element and the corresponding set element in the public key. So in this case, for example, the adversary guesses A1 is color blue, and it generates in such a way that it knows the discrete log between A1 and X1. Okay, so how many colors there are? There are P colors, so the adversary can guess a color correctly with probably 1 over P, and the adversary needs to make the guess correctly for N set elements, so that's how we arrive at P to the minus N. However, there are some complications. First of all, you can say that, okay, so if there is an edge between two public key elements, right, that will give you less colors than you actually have. And we show that we can take care of that with the minus P over T term. And on the other hand, the adversary, while we require the adversary to have these required edges, but the adversary can potentially, when simulating a graph, can add additional edges. We show that these can be taken care of with this additional minus 1 over poly term. So this is sort of the very high-level idea of our proof outline. But formalizing this is highly non-trivial. The main technical challenge here is that the honest parties, they can run some identification protocol just on the side without using the group action oracle. So in the proof, we have to give the adversary unlimited amount of private computation, so it's computationally unbounded. The only hardness comes from bounding the adversary's number of queries to the group action oracle. So if you're interested in the actual proof, I would recommend you to take a look at our actual paper. Okay, so to quickly sum up, in this paper, we show a lower bound of lambda squared over log lambda for group action-based signatures. And this actually matches the state of the art of group action-based signatures constructed from isogenies. And, but we want to notice that there are several possible ways to circumvent our lower bound. So one possible way, because what we showed is a lower bound for ID protocols. So if we're able to build a signature scheme that is not based on ID protocols, then our lower bound no longer apply there. Or you can try to make a construction where you use the group actions non-generically. For example, a isogeny-based signature scheme called ski sign actually makes non-generic use of group actions, and their signatures are pretty short, like 200 bytes. Or you can bring other hardness assumptions, and then our lower bound won't hold. Okay, so that is the talk. Thank you all.
Okay, we have time for one quick question, yeah?
Hi, Thank you for your talk. I was wondering if you considered, in fact, group actions that are not based on isogenies, and how are those related to your lower bounds, if you have an intuition on that?
Yeah, so for group action not based on isogenies, I think so far the constructions are also by constructing an ID protocol first and then transferring to a signature scheme, so our lower bound still holds there. So we bring out isogenies because it's a main dominant way of getting group actions.
So I was wondering, there's recently been this algebraic group model formalization for group actions. Does your bound carry over to that model?
Our bound is proved in the Morris model, so I'm not sure about the specifically how this algebraic group model compares to Morris model, but yeah, that's a good question. We will need to check that.
Okay, thanks.
Okay, yeah.
Okay,
thanks.
thank you all.
Let's thank the speaker again. All right, so the next talk is called Short Signatures from Regular Syndrome Decoding in the Hat by Eliana Carrozza, Geoffroy Courteau, and Antoine Jou. And Eliana is going to give the talk.
Okay.
It's yours.
Thank you for introduction, and thank you to everyone for being here with me. I'm Eliana, and I will show you a protocol on which I work in collaboration with Geoffroy Courteau and Antoine Jou. That is a new signature scheme based on regular Simeon decoding assumption and using an MPC in the end protocol. So for defining this signature, we first defined a zero-knowledge proof of knowledge, and later we switched to a signature using Fiat-Shamir. So let's start with refreshing some definition. First of all, what's the problem? Okay. First of all, what's a zero-knowledge proof of knowledge? Is an interactive protocol between two parties, a prover and a verifier, and the first one wants to prove to the second one that he knows a witness, but without revealing any information about this witness. So we defined this protocol, and we switched to a signature later. What's a signature? In a nutshell, is a common standard, is a way to be sure about the authenticity of someone's identity. So in the classic cryptographic setting, which we have Alice and Bob, how Bob can be sure that a message is really sent by Alice. As in real life, it will be enough for Alice to put a signature on it. Also, digitally, she can do it using an authentication mechanism. And currently, there are a lot of signature schemes, but how you probably know, the advent of quantum computer will destroy all of them. So for this reason, the NIST introduced the famous competition to define new post-quantum cryptographic assumption based on mathematical problems that are supposed to be resistant against quantum attack. And between all these problems, we work with the syndrome decoding problem. That's the following. We have three parameters. Two of them are dimension for a parity check matrix H, and the last one is a value W. We have this parity check matrix and a syndrome Y, and we want to find a vector X such that H times X is equal to Y, and the Hamming weight of X is equal to W. So, of course, we can add some properties that the solution vector has to satisfy, for example, regularity. This means that the vector can be divided in W block, and each of them has Hamming weight equal to 1. So we worked with the regular syndrome decoding problem, and for better use this problem in our protocol, we decided to look at these two conditions in a different way. That means over two different structures. So the first one is defined over F2, and second one is defined over a larger ring that is ZT. So how you can see these two equations are nothing else linear conditions that have to be satisfied. So for this reason, it was really a natural idea to decide to work with the MPC, because in a multi-party computation protocol, everything that is linear is really simple to be obtained, essentially for free. How this is possible? We have n parties, and each of them has a private information. So a multi-party computation protocol allows them to jointly recompute the image of a public function over all these inputs, all these n inputs, but without revealing their private information. So for this reason, the use of the MPC in defining new zero-knowledge proof of knowledge was already founded in literature as the MPC in the head. So suppose that we have a public value y and a public function f, and the prover, of course, he knows a witness x, and you want to prove that he knows this witness such that f of x is equal to y. Then what he can do, he can split this witness between an imaginary part in his head, and later he can use the MPC over a new function, g, that is related to the public function f. So in our case, what are the public values? We have the syndrome y and the Hamming weight w. So we can define the public function f of the witness x as h times x mod 2 and Hamming weight of x mod t. And in this case, our prover can share the witness between n parties using additive shares. And later, he can define a new function over all these n input as the public function f, but computed over the sum of each party's information. Of course, over the right structure. So what's happened in detail in prover head? We have these n parties, and each of them has what we call it a view. The view is made by its share of the witness. So for party PI, we have the share xi. And in the online phase of the MPC, each of them can compute the image of the public function f over the private inputs. So for party PI, he will compute h times xi mod 2 and Hamming weight of xi mod t. And the verifier later can check that the prover was honest by asking to see all parties' view but one. This is because, if the prover is not honest, so he doesn't really know the witness, he must have lied at least in one party's view. So he has many chances to be caught by the verifier. And in the same time, however, revealing all parties' view but one doesn't allow the verifier to recompute the witness. Because as you can guess, to recompute the whole value, we need all parties' view. So this is totally secure, and it's really simple because, as you can see, there are only simple sum, so everything is linear. The only problem here is that in the online phase, each party has to compute these two values using the public function, but the first one is computed mod 2, so this means that party needs a share of the witness mod 2, and second one is computed mod t, so this means that they need share of the witness mod t. So what we need here is a mechanism to convert share of the witness mod 2 to share of the witness mod t. And we discovered that we can easily obtain this by using a random vector R to define a new vector that is an auxiliary vector, z, computed by using the share of the witness mod 2 and share of the random vector mod 2. So in this case, we can switch to the share of the auxiliary, the witness mod t by using this formula in which we have a share of the random vector R mod t. So this means that if in our protocol there is a third trusted part, that before the online phase of the MPC starts, he gives to all parties what we call the preprocessing material, that is share of the random vector R, mod 2 and mod t. Then everything will perfectly work because each party can use its share of the preprocessing material to apply this formula and to obtain the share of the witness mod t. But the problem is that we don't want to add another part in our protocol. So we decide to allow the prover itself to share the preprocessing material. This means that in the first round of our protocol, the prover has to share both the witness and the preprocessing material. And of course, he has to compute to all parties' view. So the second round is for the verifier to check that preprocessing phase was well computed in a way that I will explain in a few moments. And the third round is for the prover to run the online phase of the MPC in the head. So each party computes the public function over its private input, as I described in the last slide. The fourth round is for the verifier to choose a challenge in a way such that the prover has to open all parties' view but one. So here, the last round largely dominate our communication cost because in all parties' view there is the share of the random vector mod t. So this means that the communication cost depends on t. And if we had chosen to work with the syndrome decoding assumption, then t would have been to the total length of the witness, that is bk. But working with regular syndrome decoding assumption, t is equal to the length of each block in which the witness is divided. So it's bk over w. So this means that paradoxically, the higher is the weight, the lower is the communication cost. And this is why we decide to work with a regular assumption. So now that the basic structure is clear and why we decide to work with the regular assumption is clear, we can figure out how we can handle the preprocessing material because, as I said, okay, if there is a third trusted part that shares the preprocessing material, everything will work, but later I said, okay, no, we allow the prover itself to share the preprocessing material, and of course the prover is not a trusted part. So how we can handle it? Okay, in literature there are two standard ways to do this. The cut and shows technique, that in which the prover has to commit many instances of the preprocessing phase, and the verifier has to open a subset of them. But this is impractical because it induces a large overheads. The second one is the sacrificing technique, but unfortunately is customized for specific type of preprocessing material. So we cannot use these two techniques, but we can handle the preprocessing material without checking on it, but with this trick. We decide that it can be used only after he is shuffled using a permutation that is chosen by the verifier. So what we had before is that the solution vector has to satisfy these four equations. So h times x is equal to y. Later we can compute the auxiliary vector using the witness and the first part of preprocessing material, s. And so switch to mod t using the second part of preprocessing material, that is t. And this new vector, x first, has to have a Hemi weight equal to w. Now that we introduced the permutation, we still have these four equations, but of course the preprocessing material is shuffled before it can be used. So a malicious prover that doesn't really know the witness, but he wants to be accepted by the verifier, he has to find a preprocessing material that allow him to obtain these four equations. These four equations are still satisfied, but without knowing in advance the permutation. So we analyze this probability, and we call it combinatorial bound. Even if it's small, we observe that this combinatorial bound becomes bigger if the verifier shows, the prover shows a witness that is regular in all blocks but one, because in this case he can find a preprocessing material that is regular in each entry but one. with probability 1 over W, when the preprocessing material is shuffled, the incorrect entry of the preprocessing material perfectly match with the faulty block of the witness, so they correct each other, they hide each other. And okay, even if, and the prover of course will be accepted by the verifier. Even if 1 over W is really small, it largely dominates our soundness error. So for this reason, we decide to allow this type of witness and to relax the regular condition. And working with an F almost regular syndrome decoding problem, in which the goal is to find an F almost solution. That's a vector that is regular in each block, except at most F. And of course, this leads to a gap between the real witness that the prover, the honest prover has, and the witness that can be extracted by a malicious prover. And we will find this gap in the soundness error. So anyway, this will not change anything in our protocol, because we will choose parameter in a way such that the almost RSD is so injective that the only almost regular solution is exactly the regular one. So nothing will change. And now that all the basic idea, all the main idea are clear, we can look in detail to our protocol. So parameters are always the same. We have the parity check matrix and the stringent, and the prover also node witness. So in the first round, he shared both witness and the preprocessing material and commit to all parties view. The second round is for the verifier to choose the permutation that the prover has to use in the online phase of the MPC in the head, and where the share of the witness mode 2 are used from each party, by each party, to compute age time x. And the shuffle preprocessing material is used to define the auxiliary vector z and to switch to mode t in order to compute the Hamming weight mode t. So this means that at the end of the online phase of the MPC in the head, each party has a message that contains a little information about the syndrome, information about the auxiliary vector, and information about the Hamming weight. And later, the fourth round is still for the verifier to choose a challenge, so the prover has to open all parties view but one. And in the verification, the verifier checked that everything was well computed and, of course, was consistent. So this means that the sum of each party's information about the syndrome has to be equal to the total syndrome, mode 2, and the sum of each party's information about the Hamming weight has to be equal to the total Hamming weight, mode T. Okay, so this, of course, was our first draft, and we added a lot of optimization, but at the end we obtained our zero-knowledge proof of knowledge, for which we can compute the soundness. Of course, as expected, this is influenced by the gap that is introduced by allowing the almost solution. And so the soundness will depend on the combinatorial bound, P. And also we can compute the communication cost. And this the biggest part of this communication cost is, as expected, related to open all parties view. And so from this zero-knowledge proof of knowledge, we obtained our signature scheme by using Fiat-Shamir. That is a common way to switch from an interactive protocol, in which we have a prover and a verifier, to a non-interactive one. Simply by computing the two challenges that before were chosen by the verifier in a random way, for example, using a pseudo-random generator. And that's what we did, really common, standard, nothing special, but we obtained our signature, and we obtained the best set of parameters that are the following. And for different value of the number of iteration in the signature and number of party in the MPC, we obtain a different signature, the faster one that has runtime less than 3 milliseconds, and the shorter one that has signature size less than 9 kilobytes. So that's really competitive with the state of the art. And that's all. Thank you for your attention, and other developments are in the paper.
One quick question. I think we have a minute or something. I have a quick question. So, do we have an overall security theorem? Like, if assumption A is true, then the signature scheme is secure?
What? Sorry, sorry?
Do you have like a general security theorem that states the security of your scheme? I might have missed that.
I mean, the security is related to the security of MPC and of the zero knowledge proof that we created, and later we just used Fiat Shamir.
Okay. Mm-hmm. Nice.
So, yeah, it's related to this.
Okay, good. Okay. All right. So let's thank Eliana again. All right, so the last talk before the track switching break is the return of the syndrome decoding in the head by James Hove, David Joseph, Nicolas Gamard, Zhongzhe Yu, Carlos Aguiar Melchior, Andreas Hülsing, and Nicolas will give the talk.
So thank you for the presentation. I'll present the paper on the return of the SD in the head. So SD in the head is not related with the isogeny one that will be broken in the next session. It's completely different. And actually, it's very related to the previous talk. So this talk is about an optimization about MPC in the head that we call here hypercube MPC in the head. So how to make MPC in the head faster and keeping the same proof size. And the second part will be an application to the syndrome decoding problem. So it is actually not the first time we see syndrome decoding and MPC in the head together. So that would be episode 2 or 3, so hence the title, The Return of the Stith. So part 1, hypercube MPC in the head. So how can we make digital signature faster, smaller, and more secure? So the good thing with MPC in the head is that we have a straight line between any hard problem that we can take as a basis. This hard problem, so we usually choose it from the NP class, so hard NP problem means something that is hard in average, but has an efficient verification function. So the verification algorithm, we are just going to run it in a semi-honest MPC mode. So then MPC in the head will turn this semi-honest execution into honest verifier zero knowledge proof between a prover and a verifier. So this time the prover can be malicious. And then Fiat Shamir will transform it into a non-interactive protocol and essentially a signature. So in this talk, we improve MPC in the head to make it faster, basically. So let's go over this chain. So I'll keep the hard problem for later, for the second part. Let's suppose I have a verification algorithm to implement. So first, I have to implement it in MPC. And here, the good news is that I can pick any MPC framework I want. Any number of players, the more the better. So we all know that 2-player MPC is very hard to put in place. But after 3 players, it becomes quite natural. We can target only semi-honest security at this step. It's okay because MPC in the head will regain malicious security later. And even a trusted dealer setup is okay. So if we have to use Beaver triplet, for example, that's perfectly fine. We'll just provide any triplet as part of the inputs and make sure that the algorithm checks for the triplet consistency. So Beaver sacrifice, cut and choose, all of that can work. So all of that means from the MPC point of view, there is no restriction. We can operate in the fastest and most concise out of all the MPC available out there. So it's just whenever we are coding the MPC algorithm, the guideline is strongly optimized for input and number of bytes of communication. The rest is a bonus. Running time and rounds, it doesn't really matter for MPC in the head. So then, once we have this MPC protocol, how do we turn that into a zero-knowledge proof? Well, the idea is quite simple. The prover will first simulate the entire MPC protocol of the verification algorithm in his mind, in his head, and basically commit to everything that is secret in the protocol, so basically the inputs, and publish everything that is public, the broadcasted communications. So then the verifier will first do a basic syntax check to verify that it looks like an NPC protocol and that the result is really 0. And then ask the prover to open n-1 of the n parties. So of course, the prover, we cannot open the n parties because that would leak completely the inputs, but if we open just n-1, that's fine. We get no information about the inputs. And then the verifier will just reevaluate these n-1 parties entirely and verify that the commitments are okay and every communication that was published on the built-in port was the right one. That means none of these n-1 parties have cheated. So the only way for a prover to cheat was to cheat on the last party that was not chosen by the verifier, so that gives a 1/n cheating probability. So at the end of the line, the verifier has learned nothing more than what a coalition of n-1 parties would learn. That means nada except the results. And the soundness is 1-1/n. So let's dive into a little bit of more details here. So we have the input shares of the n players. So usually on the inputs, we have the actual input of the function that we call the witness, and we have some beaver triples. So inside the beaver triple, there are some uniform random variables, and there are some dependent variables. So the prover will just secret share that. So from a secret sharing point of view, everything derives from a seed except the last share. And even inside the last share, the uniform part still derives from a seed. So that's something that is still small. The prover will publish a commitment on the input. And then if we look at the MPC protocol right in the eye, what is the MPC protocol? It's just going to evaluate a sequence of linear functions one after the other. And each function will have a result that is revealed. So let's say the first function is f and the result is alpha. Since the function is linear, every player will publish a share of alpha that reconstructs to the plain broadcast alpha. And then alpha will be used to parameterize the next linear function. So second one will be g alpha that will produce shares of beta and reconstruct to beta and so on until we execute the last function, z of alpha, beta, gamma, delta, whatever, blah, 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 that will give the shares of the final result. And in the case of a verification, this result should be 0. So here in this picture, everything that is in green is considered public and published by the prover. And everything that is in gray is secret, so only n-1 will be open. So of course, that would be a lot verbose if we do that. So in practice, we realized that, well, someone realized in the past that it was not necessary to publish the whole broadcast board. Just the hash of the broadcast board is enough. because eventually what will happen in the proof is that n-1 colon will be completely open, so the verifier will be able to recompute it. And since we have also the plain text, we'll obtain the last colon by difference. So we only need the hash to make sure that nothing has moved. So from a proof size point of view, we are good. The only thing is that we still need to compute this broadcast built-in board, and that's the clear running time bottleneck, both during the proof and during the verification. So in our work, so we realized that before we had to do n evaluation of the MPC protocols, one for each party, and that was the bottleneck. So in the optimization that we propose, we realized that we actually only need to do log of n evaluation of the protocol. So that becomes negligible. And the main idea is that before we had to evaluate the MPC for each individual party, and in what we propose as the hypercube MPC in the head, we can actually group parties together, make log of n groups of n over 2 parties, and as long as the group are, I'd say, independent, we are fine. We'll get the same soundness in the end. So let's try to give an intuition of how this can work. So let's take a 6-party protocol. Each party has one share of the input, x1 to x6. So from what we just said, when we compute the built-in board, if we do individual evaluation of the MPC protocol, we will have to do 6 evaluations of the broadcast board, and that will get a chance of cheating of 1 over 6. Then, okay, we can say if we take the sum of all the contribution of all the parties, we get the plain text x, and we can decide to evaluate the plain text. So since all the intermediate functions are linear, we get the plain text, plain broadcast, alpha, beta results. And if we have the plain text, it means that instead of evaluating 6 parties here, I get 1 for free, because the contribution of the last party or any party is just the difference between the plain text and the other contributions. But yeah, that's just a strange reduction here because I still have to evaluate the plain text, so it still counts as 6 evaluations. So what can I do better than that? Well, I could say, instead of considering 6 parties, let's consider 2 groups of parties. The rows, for example. So group 1 that will contain x1, x2, and x3, and starts with x1 plus x2 and plus x3, if we have an additive scheme. And the second group that will start from x4 plus x5 plus x6. And now I can view my MPC protocol just over these 2 groups instead of 6 parties. So I have the red execution that contains 2 lists of broadcasts, and if I already have the plain text, I can strike 1. So, well, is it better? Well, not quite yet, because now the chance of cheating is 1 over 2. 1 over 6 was better. But now it becomes to get interesting, because I could now decide to do exactly the same thing with the columns. So now I have 3 blue groups. One that starts from x1 plus x4, the second x2 plus x5, and the third x3 plus x6. So I can do exactly the same. Here I will have 1 chance over 3 of cheating. And something that is really nice here is that we can prove that somehow the blue group and the red group are independent, which means that if I do the red and the blue computation, the chance of cheating will multiply. So I will have 1 over 2 times 1 over 3, that's 1 over 6, which is the same as the black one, except that if I count the number of evaluation, I only have 1, 2, 3, plus the green one, so 4 evaluations instead of 6. And so of course, not all partitions of parties are independent. For example, the red and the black are not independent, so I cannot get 1 over 12. There are some bounds and some conditions, and If you look at the proof on the paper, that will be more explicit, but yeah, that's really the intuition. What I did with the rows and the columns in 2 dimensions, I can do it with a cube in dimension 3. So take parties by x coordinate, y coordinate, z coordinate. And I can also do it in dimension 4 with a tesseract, or in dimension t. The bigger the dimension is, the better it gets. So yeah, the best setting that we can have is a d-dimensional hypercube of size 2 for 2 to the d parties. So yeah, that's the main idea. So if I do a single execution of MPC in the head, I get a 1/n chance of cheating, so that's log 2 of n bits of security. With our work, since the bottleneck is not a bottleneck anymore, we can also say that if we allow to consume the same running time as before, we can take n larger. So with the same running time, we get more security. Now, of course, the idea is not to get log of n security, but it's to get lambda bits of security, where lambda is a fixed security parameter. So it means we will have to repeat the process. So that's parallel composition. And if we have more security from the base, we can do less repetitions to achieve lambda. So less repetitions means faster proof and also smaller proof, because each repetition will contribute to the size of the proof. And once we have zero knowledge proof that achieve lambda bits of security, we just end with a Fiat-Shamir transformation that will make it non-interactive and transform the proof into a small signature. So during the last conversion, there is just some things to make sure that any attacks that was sequential before can work in a parallel setting. So that's Hypercube MPC in the head. And now let's dive into Hypercube SD in the head. So the only thing that we miss is the original hard problem. So of course, in the NIST competition, we want something that is as strong as AES. So we could say, let's take AES as the hard problem, and that would solve the loop. So the problem is that evaluating AES in MPC, it's fast, but not fast enough so that we can make a good signature out of it. So let's try to go in the literature and find another good hard problem. And one of the things that we can take is really this syndrome decoding problem. So solving the equation hx equal y, where x has a small Hamming weight. So this problem has been around for a very, very long time. There are a lot of cryptanalysis on this that was done, and now we are quite confident that what is exactly the hardness of this problem, even for quantum adversaries. So the nice thing is in this program, so verification function, even in this form, that would already be very efficient in MPC, but there is actually an equivalent formulation of the same problem that use polynomials. So basically, when I have h and y, instead of just finding x, I will look for a prefix of x plus 2 polynomial of small degrees, p and q, that satisfy this formula, so that this big polynomial is 0. So to convince you that it's approximative, well, it's exactly the same as before, yeah, you can see that this right term will evaluate to 0 over 1m. So if the equation has to be 0, it means that the product of the two terms here is 0. And if it is 0, it means that x that is here can only be non-zero over the roots of q. And since q has a small degree, the Hamming weight of x is small. And vice versa, the reverse is also true. But the very nice thing with this polynomial form is that once you have a polynomial and you want to prove that this polynomial is 0, that becomes very easy. You get very efficient randomized verification function. Basically, you just the verifier will just ask the prover to evaluate the polynomial in one random point that the verifier chooses. And if we get 0, then there is a very high chance that the polynomial was 0. Because if you have a non-zero polynomial, getting 0 would mean that the verifier has by accident found the root of the polynomial, which has a very small proba. So yeah, there is a false positive probability, p, that is very small, and the soundness will be 1 minus p times 1 minus 1 over n, instead of just 1 minus 1 over n. But since we are iterating that until we reach lambda, that's perfectly fine. And to finish the presentation, so we implemented it in practice. We used actually the same parameters in the paper as the original literature on it. It gives sizes that are very reasonable in practice, so SD parameter of less than 500 coefficients. In MPC, we'll target something like between 16 and a few thousand parties. We have to work in some extension field at some point. And the thing that is really interesting is that so there was always a trade-off between the number of parties we take in the MPC in the head protocol and the number of repetition that we have to do to reach lambda byte of security, so it looks like 1 over x function. And before, we could only use a very small trade-off about this curve because the complexity of MPC in the head was really killing it. And now that MPC in the head is faster, we can push the trade-off much further and get proof that are shorter. And the size of the proof really matches the size of the digital signature that we get in the end. So we are talking things like 8 kilobytes, 6 kilobytes, 5 kilobytes. So running time, well, it's really practical. So depending on the size of the signature we target, we'll have something between 1 millisecond and 200 milliseconds. So it's far less than 1 second. And that's it. So to conclude, this gives the possibility to give new post-quantum signatures based on any problem. But if we take SD, we have a candidate, a signature candidate that we're going to submit to the June deadline together with the original authors of other goodies about that. It's a signature with microsecond latency, so on the offline-online phase model, it's very good. And there are still some open problem and limitations, so we cannot take n exponential, the number of parties, because the state generation is still linear in the number of parties. And that's it. So thank you very much for your attention.
So thanks, Nicolas. We have absolutely no time for questions. So now there is a track switching break, which is only 6 minutes. So we reconvene at 11:40.